Hi everyone, welcome back. Today I'm going to be talking about the properties of limits. So basically, we already know one thing we need to know about the properties of limits that is going to help us out here is that if the left-hand limit and the right-hand limit are both the same, then the limit exists and that is our limit. If they are not the same, the limit does not exist, right? So just a reminder of that fact is going to be very important. Also, whenever we have a non-piecewise function, just a function that is continuous throughout, all we need to do is just plug in the value, right? So here in this example, in this first example, example 1, it says determine the limit as x approaches 5 of this function. Now clearly, this function is continuous at x equals to 5, right? And so in this example, all we need to do is just plug in 5. So I'm just going to say, okay, well, that means root 5 squared over 5 minus 1, which is root 25 over 4, which is root 25 over root 4, which is 5 over 2. So therefore, limit would just be 5 over 2. And we're done. Okay, let's move on to this one. It's a little bit trickier. It says, determine the limit as x approaches to 4 and sketch the function. So for this example here, it's a little bit different because I can't just sub in x equals to 4, otherwise I'll get something undefined and I'll think maybe my limit doesn't exist, which is not the case. This limit actually does exist, even though it is true that f of 4 of this function, right, the function as when x is 4, that is undefined. This function is undefined at x equals to 4, but that does not mean that the limit doesn't exist. So to find our limit, the first thing I'm going to do is I'm going to factor this. I'm going to say this is the same as x minus 6, x plus 6, x minus 4 over x minus 4. And then these cancel out and we just have the limit as x approaches to 4 of x plus 6. So what we really have here is, what we really have here is a what? What we really have here is just a line with a hole in it, right? Just a line with a hole in it. And so let's see, 1, 2, 3, 4, 5, 6. So let's say this is 6, 7, 8, 9, 10. This is 10. We just have a line with a hole in it. We start it here at x equals to 6, and then we go up, and this is where our hole is, right? So we just have a line with our hole in it. So there's my sketch. And so there at this point, we can now just plug in our value of 4 and get 4 plus 6, which is 10. So this limit is 10, right? Because in terms of when we're approaching 4 from both sides, we are going to end up with 10, even though we're undefined right at x equals 4, right? Because that's the big difference between a limit versus just plugging in, some number in a function, which we've done previously, right? Is limit has to do with what's going on around the space, which also sometimes does include what happens at the space, like in example 1. But other times, like in this case, f of 4, right? It's undefined, right? But what's happening around x equals 4, that is approaching just that one spot because this is a hole. Now, what about this example here? We have determine the limit as x approaches 2 of this function. Well, remember that an absolute value is really just a piecewise function, right? That states that there's two possibilities here. Either the limit as x approaches 2 from the left, which is going to be where we have a negative, right? Or this could equal limit as x approaches 2 from the right, which is going to be x minus 2, right? Positive x minus 2 over x minus 2, right? Because again, the absolute value function is just a piecewise function where half of it is negative and half of it is positive, right? This just tells us the distance from 0. So let's continue to solve. Here if I, Keep doing that. If I cancel these out, I'll just get limit as x approaches 2 from the left is minus 1. And here I'll get limit as x approaches 2 from the right is 1. And then what we do is we just plug 2 into these equations. Now there's no x to actually plug in anymore, so that means it's just going to be minus 1 and 1. And if you'll recall, those are different numbers, and so the limit does not exist, right? Limit DNE for does not exist. Now we can still draw this. We can still say, over here we have plus 1, and over here we have minus 1. So here's how I would draw this. And I'll label a couple points there, like 1 and minus 1. And also I should mention that this is 2, because that's the other key point here, right? That's how I would draw it. And clearly from the drawing, we can see that they don't approach the same point. There's clearly a jump here. And also the function is clearly undefined at x is equal to 2. Since we only have holes, we don't have a single filled in point. And that also makes sense with our original function, right? Because if x was equal to exactly 2, right, we would get 0 in the denominator, and we can't have that. We can't have 0 in the denominator. Awesome. So let's try another one. I think I have 3 more examples for you today. This one says determine the limit as x approaches to 0. Now, of course, we can't really do that, right? We can't really just plug in x is equal to 0 right away. And it says we're going to be using a change of variable. So what I'm going to do is I'm going to recall that u cubed minus 8 is equal to, right? If we let u, I should define my variables first. Let's let u equal to x plus 8 to the power of a third. So therefore u cubed would be x plus 8, and therefore x would be equal to u cubed minus 8, right? Now, when we say as x goes to 0, we'd be saying, well, as u goes to 2, right? Okay. So now what I'm going to do is I'm going to recall that u cubed minus 8 is equal to u minus 2, u squared plus 2u plus 4. And just because u cubed minus a cubed, right, for any difference of cubes would be u minus a. Oh, sorry, I should not u times a, u minus a, u squared plus au plus a squared, right? So that's just a generalized equation. And now we're going to solve this. So we're going to say the limit as u goes to 2 of u minus 2 over u cubed minus 8 is equal to what? Is equal to u minus 2 times u minus 2 u squared plus 2u plus 4. And then we cancel those out. We're going to get 1 over u squared plus 2u plus 4. And now we can plug in 2, right? We're going to get 1 over 2 squared plus 2 times 2 plus 4, which is going to be 1 over 12. And so 1 over 12 is our answer using those change in variables. Okay? All right. Now I have a couple other examples where we're using our change in variables as well. Let's try this example here where we want to determine the limit as x approaches to 27, x to the power of a third minus 3 over x minus 27. And again, we need to use our change in variables here because if we just plug in x is 27, we are going to get nowhere. We're going to realize that it is undefined at that point and therefore discontinuous at that point. So in this case, let's let u equal x to the 1/3. That means u cubed is equal to x. So as x is approaching 27, u is approaching just 3, right? Because the cube root of 27 is 3, right? Now limit as u approaches to 3 of u minus 3 over u cubed minus 27. That's going to be equal to u minus 3 over u minus 3 times what? Times u squared plus 3u plus 9. And that's based on the same equation we used up here. We're just repeating that again with our new variables that we have now. Then we're going to cancel these out, and we get 1 over u squared plus 3u plus 9. And that is equal to 1 over 3 squared plus 3 times 3 plus 9, which is equal to 1 over 27. And there's our answer. All right. Last but not least, let's try this one using a change of variable, and then that will be it for our unit. So here it says, determine the limit as x approaches to 9 in this case. So in this example, let's note that the root x is equal to x to the power of a half. Let's let u equal x to the half, which means u squared is equal to x, which means as x is approaching 9, u would be approaching 3, right? Because the square root of 9 gives us 3. Now let's plug in those values. This is equal to the limit as u approaches 3, u minus 3 over u squared minus 9 is equal to the limit as u approaches 3, u minus 3, and then this is just a difference of squares, so u minus 3, u plus 3, and then we cancel these out and we just plug this in. And we get that the answer is 1 over 9. Or sorry, 1 over 6. My apologies. 1 over 6. And there we have it. That's it. All right, well, that is the end of our Unit 1. Next time we'll be doing Unit 2, which will be talking about derivatives. In the derivative unit, we'll talk all about the finding derivatives from first principles, but we'll mainly be focusing on things like power rule, quotient rule, product rule, and chain rule. Especially chain rule, that's a good one. And yeah, that is pretty much that.